Hi, whoever is there, are there two people? I hope it's not just me. Hello. So we have three people, right? So what happened in the same series of last time is I opened this problem. One viewer. That's just me. Hi Vedant. So yeah, we will try to solve some problems. Uh, Currently I'm at like 2100, I guess, rating. But 2100 is interesting, right? My tongue is hurting. 2100 is interesting, right? Yeah. So guys, in this series of solving one problem in each rating, where we are now is at 2100. And last time what happened was, in the last stream I opened at 2100, but then I got stuck in it. I got stuck in this problem. So the stream, I took one and a half hour or so for this, but I haven't solved it. But now I have one idea on this problem. Okay. So I will briefly go over this, and then I will choose some other problem to solve the problem. Okay. I'll just briefly explain this. I won't solve it wholly, and then I'll try to go to some other problem. Okay. Try it if you want to see. Mm, I can try to do that too, but let me solve at least 121 or 122, because the stream name is like solving part 4, right? It's part 4 of the previous series. So try to follow this up, Vedant. So in here, what happened last time was I was making some random. Let me open that folder. Solving each trading. 1 minute. I have that. This one. So this I gave some explanation. This is another 2100. So for that 2100, I gave some explanation, but I haven't solved it. And this I got stuck in, which is make it equal. You can probably see it somewhere here. Make it equal. Yeah. So I was going on trying to write linear equations and all, but in discrete things, linear equations doesn't help at all, I guess. Most of the time they won't help because it's discrete, right? So let me try to solve it using one small observation. First I'll explain the problem. Yeah, let's see the problem. So the problem goes by this. Okay. Try to Vedant, you're there, right? Try to try to understand the problem. We have a cyclic array. Okay, we have a cyclic array, and in one operation we can do ai by 2, and then the next thing you have to increase plus 1. So it's like we have a cyclic array of values being there. What you can do in one operation is you can reduce something by 2, and then you have to increase something by 1. This is one operation. The next thing you have to increase. That's the operation. Okay. And now they are asking if you can make everything equal or not. And then they are asking calculate the minimum number of operations to perform. One thing is very clear. After one operation, total sum reduces by 1. That's clear, right? After one operation, total sum reduces by 1. And we have to make it all of them equal. I unnecessarily tried writing some linear equations and then making them equal and all, but I think we can write such a simple one fact we can say. If we look at maximum in this cyclic array, it must reduce, right, at least once. So if all elements are equal, we are done. If all of them are not equal, maximum must reduce, right? Maximum must reduce. because if maximum never reduces, we cannot have everything becoming maximum finally, right? Because sum only reduces, so we cannot have everything equal to maximum. Just this small logic gives us a solution to the problem. Do you guys get how? Because now we know one operation that we can do, which is minus 2 on max plus 1 on the next thing. And that must be done. And sum reduces by 1 with this operation. And we cannot keep on going because we cannot make everything anything negative. We have to have everything non-negative, because if you see, we have to make them non-negative equal integers, which means if we keep going, if we keep doing this operation again and again and again, find maximum minus 2 plus 1 minus 2 plus 1, find maximum minus 2 plus 1 minus 2 plus, if you keep doing that, you will eventually return to a place where some of them is 0, or you may make everything equal. So this is a solution. Complexity is bad, but that is far better. This is a far better solution than trying to apply linear equations and all, because they never help. Linear equations wouldn't help in discrete cases because we have integer constraint, right? That our answer should be an integer. So they won't help. But just this fact is giving us a solution. Complexity is too high, but this is a solution, right? So I won't go further in trying to solve this problem because it may again ruin the stream. I will try to choose some other problem. But what I'm telling is just such a small fact that okay, maximum is not reducing; it must be reduced. Max maximum can must be reduced itself. Minimum may increase, minimum may decrease. We don't know, but maximum must reduce. And in our operation, minus 2 plus 1 says minus 2 must apply here at least once, so we can proceed further to the solution. Do you guys get what I mean by this? So we'll try some other problem, but that's it about the last problem. Is that a bit okay, Shvedant? I respects. Yeah, right. So let's. It's just 7 minutes into the stream, and let's. This looks makes me looks not that good. Mm, let's try to open a new 2100 problem and try to read and try to see how we can do that. Okay. So guys, five viewers, we are trying to open a 2100 and then we're trying to see how difficult it can be or how easy it can be, how nice it can be or whatever. So this was the one I opened, right? But I think uh, I'm scared of such divisor problems many times. For two integers x and y, we will say x is generator of y. Haven't I not solved this problem? See, I think I have tried this problem, guys, so we won't try it again. November 9th, 2024. Have I tried this problem before? Yeah, so let's try sometime and then we can think. And then we can think to choose some other problem because we want to solve 120, 100. That's the only restriction here. If this is being not too good, I will skip it. But let's try to read this problem because we should not get scared of problems. Reading them is half the solution. Uh, for two integers x and y, we say that x is a generator of y if and only if x can be transformed into y by choosing. Okay, I got stuck in this problem. I tried it a lot, but then I got stuck in this problem. But then I saw the solution, I guess. I saw the solution in someone's code, I guess. Maybe in Jiangli's code, I saw the solution. Uh, I remember that. Is this my rated contest that I fucked up? You guys can see how I fuck up contests. A, B solved at 20. Was I not able to solve A? Okay, it got. Okay, I wantedly resubmitted A to get more negative, so I fall back to candidate master. Here, I wantedly resubmitted A so that I fall back to candidate master so that I can give the next due to become a bit higher rating. See the gamble I'm doing. Is it going right now? but I don't think people will be interested. But this stream I cannot. I would have tried it if tomorrow, like yesterday's contest. But yeah, so this I have seen the solution, so we will not try that. I know solution a bit to that problem. Uh, should we try this token removing or apple tree traversing? Yeah, maybe let's try this problem. Okay, let's try to read this problem because I have solved the other one. I just closed it. So let's read this problem. This I haven't seen at all. There is an apple tree with n nodes. Initially, one apple at each node. You have a paper with you. So, guys, if you guys are scared of tree problems or graph problems, they don't use anything. It's all just logic. So, you have to read the problem well. We have an apple tree with n nodes. Initially, one apple at each node. You have a paper with you. Initially, with nothing written. You're traversing the apple tree by doing the following action as long as there is at least one apple left. Choose an apple path UV. A path UV is called an apple path if and only if for every node on path there is an apple on it. So we have what an apple path is. Let D be the number of apples on the path. Write down three numbers D, U, V in this order on the paper. Then remove the apples on the path UV. Here, the path UV refers to the sequence of vertices on the unique shortest walk from U to V. Let the number of sequence on paper A be paper A. So the number sequence on paper B A. Your task is to find lexicographically largest possible sequence A. So does this use any topic or it will use only logic? That's the one question I have for Vedant. It must use logic, right? Hello Vedant, if you're here. So we have a tree, we have apples on it, we choose some path as long as there are apples, and then we choose some path, and then we choose some path. And they are asking to find lexicographically largest. What topic can help us? Yeah, you're not very confident, so you will get confident in this stream. Okay. So it's not about graph or tree, is what you have to realize first. It's logic. It's just logic. No, there is a restriction on how you can select things. What's the restriction? You have to choose a path and then remove them. 1 minute. Uh, lexicographically largest possible sequence here, right? So we have to removing more number of apples is good, but then we write three numbers down: D, U, V. D makes some sense, but U comma V also makes some sense. So this says that, see, if it was only D, the initial path that you have to take is not unique, right? Because you can have multiple D length things. So you will write things down. You will write D U V down. It seems. Have you read the problem? My tongue is hurting because of speaking a lot. I bite my tongue yesterday, I think. One minute, guys. Like, what will I do? Why is this not working? Give me a minute. Maybe refresh. So yeah, it's not working. So what I will do is I'll add a new file. Let's make it into previous format. So, what are your views on this, Vedant? I have tried restarting VS Code. Maybe there is issue, something like that. So yeah, Vedant. So once you remove, so we choose a path u comma v on tree of length d, and then we write duv on paper. So we have our duv sequence, duv, and then again d1 u1 v1, and then d2 u2 v2, and so on. So one thing is very clear. We want this to be lexicographically maximum, which qualifies all the paths that are longest. We can have some longest paths in a tree, right? A tree can have some several longest paths. So all of them will qualify, because using any other thing would make our first element itself low. That is bad for us. So solution wise, this seems direct, right? Vedant. Solution wise, this seems direct, right? uh, what we have to do is we have to choose the longest path, and then because of u comma v, it also fixes what path should be chosen among them, right? Among all diameters also that will be chosen. And once you remove that longest path, what will happen? You have to solve the same problem for remaining things, right? Because they get disconnected now. Once you remove that path, you will have many small trees. You have to solve the same problem for all of those trees. Mm, so it's about finding this path quickly, right? We have to somehow find this path. It is a diameter, definitely, because diameter is the longest path in a tree, right? uh, Diameter is one of the, I mean, is one longest path in a tree. So if you see a tree, if you look at the longest path diameter, okay, let's say this is the longest path in the tree, okay, both of them must be leaves, right? Both of them must be leaves. What we can say is there can be other things too, which are possible diameters. There can be other things too. But one thing we can say is, if let's say this is the center, here we have two centers, right? If this is the center, all the paths that are here cannot exceed this length. Otherwise, they would be diameter, right? Also, all the paths that are here, they also cannot exceed that length, this length, and these both are equal lengths because this is the center. So we can have multiple options from this center, okay, this side, this length L, we can have multiple options among them, and this side also we can have multiple options among them, right? So among all those multiple options of maximum length, and among all those multiple options of maximum length, what we have to choose is biggest here and biggest here. Then our path would be d b u, right? Biggest on the left side, biggest on the right side. So this seems simple, but then for this the complexity is of n, right? To do this thing, we have to select these two things, and then once we remove this path, we have smaller subarrays, so smaller trees forming, right? And then we have smaller trees forming, and then we have to again solve on each of those trees. But if you observe one thing, yeah, I made an observation, also you should make an observation. So till here it's fine, right, Vedant? So let's learn a bit about diameters, okay? If you look at a tree diameter, let's say logically what we can say about a diameter. Let's say this is the longest path, one of the longest path. May not be the longest. I mean, there can be several others too. If this is the longest path, one, two, three, four, five, six, seven. here we have only one center, right? And let this length be L and let this length be L. What we can say is, because this is the longest, from here, every vertex must be less than or equals to L distance. Because if it is longer than L distance, we have a larger path. We are using logic here, like proof by contradiction type of logic, which we use several times. So we should be able to use such logic easily. So all other paths would be less than or equals to length L. But some can be equals to length L. Some other vertices also can be equals to length L. There must be leaves. If they are not leaves, we can have a bigger one, right? So we have few things equals to length L. Few things equals to length L on both sides. All of these points which are equal to length L and all of these points which are equal to length L qualify for the first pair, which is D comma U comma V. Do you get what I mean? Right. Yeah, you got that right. So, but we can do this in O of n complexity, right? It takes a lot of complexity. So first uh, we have to find the center. So let's say we found the center. I think there is a way to find the center. Once we found the center, then it's simple. You can do a simple DFS, and then you can do a simple DFS, and then you divide the tree. After center we have multiple things, right? We cannot choose two L things on here because their shortest path is not that, right? We have to choose. So let's say, let's look at the center. If this is the center, we have many L's, right? If this is L and this is L, we should not choose those two. We should choose L's from different children. That's the only restriction. Okay. So for each children, we can collect of size L minus 1, size L, maximum sizes of L minus 1, L minus 1, L minus 1. And then for this, we have to choose among all the other. For that, we have to choose among all the other. Also, this can be done. So in O of n, we can do something, right? But once you remove this thing, you have to again solve it for all the smaller trees, right? Once you remove this path, you remove all these vertices, then you have many small trees formed. You have to solve for each of them again. You have to solve for each of them. Let's say you're again solving for each of them. Their size is not halved. If you see, their size is not halved because you can have many vertices just here. Once you remove, we can have lot of vertices here. So the size is not halved. But can you say what is halved here? Vedant, something is here. Can you say that? If you look at the newer subtrees, some property of them has become half. So if our current tree has maximum diameter as length 2L, what about the maximum diameter of these things? No, that is also not being halved. That is also not being halved. I thought that is being halved, but that is also not being halved. I thought uh, the diameter of these things is L, but it is not because we can have something like this, right? This is one thing, and then you can have something like this. Both are less than L, but once you remove this, you again have a big diameter of 2L minus 2 size or 2L minus 3 size. I thought the diameter is getting halved, so we can keep proceeding further and the complexity will be low, but it's not happening. So we have to think. One thing is very clear: we must have to identify these things and then remove them, and then we have to keep proceeding on everything else. Yeah, Yeah, keep trying, I guess. We have two viewers, but you can keep trying. We can solve it because only logic can help. Here, complexity is the only issue we have, and we have to think of a way in which we can do it good. Or maybe we have to prove that complexity is not that high here. So it won't be too difficult. Till here, it's direct, right? What to do is direct. We must do that. We must do that. There is no chance for us. We must do that. But we must do that, and there's no choice for us. But once you remove that, we have to find among remaining trees. Once you remove that, you have many other subtrees, right? Many subtrees from here. On this big path, we have many subtrees. So we have to solve the same problem for each of those subtrees. We have to think. Let's try to think. Maybe we can do some. Maybe we can say something. Try, guys. I'll also try to try. So we have many small subtrees. Can we again try to find the diameter for them? How to find again diameter for them, and then again how to find the lengths of all the paths again. So it won't be too complex because 2100 cannot get complex at all. 25, 26 also doesn't get complex. So we have to, now bro, it's not that tough. It looks tough, but maybe finally the problem is simplified. We don't know. Okay. Yeah, it looks tough for me too, right? If you say that, even for me it looks tough, but what to do? See, what to do is simple here. We need somehow better complexity. This is a shit problem, but let's at least solve the problem. Let's not implement it because it looks see, once you solve it, implementation will be simple. So let's focus on solving. It's not too tough. Only logic can help us. So once you remove this, trying to see what would be the next longest path, that also can be a bit high, that also can be a bit big. So if this length is L, in this tree we have, in this tree we have largest length itself being less than or equals to L, L minus 1. One thing we can say is it's definitely reducing. The longest length is definitely reducing among the other things. See, what to do is here very clear. Bro, here what to do is obvious, right? Would you have made such statements, at least if you have tried on your own, that see, what to do is obvious here. We just have to think, try for some time. See, it's maybe some en route and shitty algorithm, bro. Maybe. Maybe some en route and shitty algorithm because 5 seconds and this much. So we have to just see about path lengths. See, en route would not be Yeah, end-to-end would logically it would not be too difficult. Maybe you split into two cases or so, right? So let's try to see a bit more because we can't use some great things here in 2100 at all. So we have to see we can have once you remove that we will have this subtrees, right? But then this subtree has everything again less than or equals to L minus 1, and then we have to find longest path in this subtree again. Let's look at it. Let's try to look at it. Okay, maybe n log n also may help or may get solved. See, we have to make sure that complexity is low. That's it. We have to prove that, little bit prove that, because maybe brute force works. That's why it's low rated. See, this problem is not that difficult. If you can see, at least the solution is direct. Just the complexity is making a bit difficult. So if you see the problem, the whole problem is direct, and all you have to do is find a way to avoid big complexity. Is it too difficult of a problem? No, right? What to do is obviously there, but if also what to do is we are not getting any clue about what to do, that's even much difficult problem, right? So here at least what to do is very clear, so we have to just think about the complexity. Let's try for some time. You have to try, bro. Maybe try, because I am also not getting anything, you're also not getting anything, but we should still try. So from here everything will be less than, from this point everything will be less than or equals to L minus 1, everything will be less than or equals to L minus 1, right? So the next value of D is less than or equals to 2L minus 1. 2L minus 2. This we can say this is decreasing, right? So if that is decreasing, let's see, let's try to say something. Okay, let's try to say something. Maybe one small point helps us, that if this length is less than or equals to root n, okay, if L less than or equals to root n, if L less than or equals to root n initially, initial L less than or equals to root n, because this is always decreasing, because this is always decreasing, we can brute force, and then it will O of n, each time O of n, each time you do O of n, and among all subtrees the maximum L will decrease by 1, so it will be O of n root n. See, this is a simple point, right? How is this point, Vedant? I mean, logically this is not difficult, right? See, I'm trying to tell you, these problems won't be logically difficult, but then they appear difficult. So you can use more logic, you can use more logic, you can think, but what they make you do is they make you get scared, they make you think it's tough. For you at least it's tough, but all you have to learn in problem solving is not some weird concepts. You have to learn that, you have to learn the ability of not getting scared and somehow do the problem. Okay, you're learning, that's what you have to learn, and if you learn that you can try any problems, right? So I'm telling in all the streams. So maybe this seems okay. Just the fact that you can see this, right? If this length be L, total length is 2L, and if you see this thing, This can be at max less than or equals to L minus 1. This can be at max less than or equals to L minus 1. Because we remove this edge now, their diameter will be at max less than or equals to 2L minus 2. So it's decreasing. Diameter is decreasing. If you see even case, even if you see even case, we can say the same thing. This is the center, right? Let this be the L. So the diameter, current diameter is 2L plus 1. Okay. From here we have less than or equals to L. If you see some subtree, less than or equals to L minus 1, less than or equals to L minus 1. Once we remove this, we have 2L minus 2, which is much lesser than this. So diameter is decreasing. That is one thing we have. Okay. Mm, see, Tech Maniac, it is always about seeing the problem clearly. Okay, if you hit dead end and all, what you have to do is try to again see the problem clearly, because problems can be solved if you follow some rules and if you see the problem statement clearly. So it's not you're getting random ideas that if you go into some bad idea, you cannot solve it again. The thing is, what you have to do is being able to see the problem well, being able to understand the problem statement, trying to see the structure of the problem statement. All these strategies helps us approach the solution. Okay, this is the way we can identify if this is the way or if that's not the way. So there are so many techniques to identify that, so many logical, small logical statements to identify that. So Vedant, are you here? So let me tell you this thing now. Okay, just this fact that this decreasing will make us solve it in n root and complexity. I got how we can solve it. Can you say how we can solve it in n root and complexity? So we have two cases, right? If we have so many subtrees, okay, if diameter lengths of all those subtrees is less than or equals to root n, can we solve the problem? Tell me that. Let's say we have so many subtrees, all the subtrees have less than or equals to root n diameters. Then we can solve the problem, because after one iteration, what happens? After one iteration, what happens? Maximum diameter of all the subtrees will again become less than 1. So if you keep going, at max you'll do root n steps. So that's n root n. Is this clear, Vedant? Hello, Vedant. No, let's make the statement again clear. I'll try to write it. So at any point we have some subtrees. Okay, let L be the maximum diameter of all these subtrees. Right. Now what we do is, in one step we will find maximum diameter of all these subtrees and remove that. So we are removing it, but then we are removing it because it may not be used right now, but it must be used sometime in the future, right? So we have different subtrees. If you remove maximum diameter from all of them, what happens is you won't use all of them right now because you have to use the maximum. But all of them, once you come to this tree, you must remove that, right? So if we do you get what I mean, Vedant? So we have to. So doing that is not bad, right? We must do that. So if you do this, the next diameter, diameter among smaller trees must reduce. This is what we proved here. Is that statement clear? Because if you see, this length is 2L plus 1, but then once you remove this diameter, what you have is 2L minus 2. If you go and see here, you have 2L diameter. Once you remove that, you have 2L minus 2. So that is reducing. The maximum diameter for everything is reducing. This is clear, right? Yeah. So, Vedant, are you here? Not too nice fun, but yeah, it's a bit nice fun. It's the n root and brute force. That's not too nice, but yeah, uh, it's at least, uh, hello, Vedant. It's at least not too difficult. I mean, it's at least not what Vedant is scared of. Uh, so these cases are done, right? If L less than or equals to root n, we can do above step O of n that takes O of n complexity, but we do that at max L times. So it's n root n complexity. So now you have to worry about the other cases. If L greater than or equals to root n of some subtree, if L is greater than or equals to root n, you have to worry about these cases. But what happens here? Can you tell me what happens here, Vedant? If L is greater than or equals to root n, what happens? We remove L elements, right? We remove L elements and throw them away, right? If you're removing L elements, how many times can you do this thing? Say how many times you can do that thing? Vedant, you can do that at max root n times, right? Because L is greater than or equals to root n. Total number of elements itself is itself is less than or equals to n. And if you keep removing L things, L greater than or equals to root n, you can do Z times, let's say. So Z into L must be less than or equals to n, but L is greater than or equals to root n. So Z less than or equals to root n, right? So you cannot do this also many times. So just a brute force solution works, and the complexity will be less than or equals to root n. Just break tree, find the diameter, add that. So just this solution. So you need not even prove this root n times, right? So now think about how difficult is this problem. It's direct. What to do is direct, and if you don't worry about complexity, you can implement it right away. If you assume, okay, I will just test my luck because solving a 2100 in contest would make you candidate master, right? So if you think, okay, I will assume my luck, I will assume the complexity will somehow work out, and then you keep doing this for each tree. Find the diameter, u comma v point, add the d comma u comma v to your possible good things, because you must add that to somewhere, right? And then you have smaller trees. Keep doing that on each tree. Keep doing that on each tree. Don't worry about complexity. Okay, so you collect all these d comma u comma v's from multiple trees. Now you just have to sort those things, because that's the optimal candidates for each trees, right? You just have to sort those trees, and then you have the sequence. Complexity you don't worry about. I would worry because I will prove before implementing. But if someone doesn't worry about complexity, they have solved the problem. the problem, that's the same solution will be unwritten. So now can you tell me how difficult is this problem, how direct is this problem, Vedant? So take a subtree, find its best d comma u comma v, remove this path, collection, let's be collection b s, add d comma u comma v to s, keep proceeding, sort s, output s, done. Complexity will be enwritten. Should you prove this? You need not. To implement the solution, you need not. But we have proved it too. We have proven it. Just because we are removing L things itself says, okay, if L is greater, you keep removing. If L is not greater, that's reducing. Done. It's too obvious and too direct. There's no great logic here to guess this. Right? That's what I mean. It was direct. It was direct. So what Code Forces does to you is not make, so problem solving is all about overcoming that fear. Believe me or not, I have been telling the same thing from my first video to now. If you are someone who won't get scared at all, you don't doubt yourself at all, you try to give your best, you keep trying, let's say, then you can do much better than what you be doing now. It's not you have to learn some secrets, it's not that you have to learn some concepts and all. You just have to improve the skill of being able to try when you're not getting anything really. So just before you thought this is too tough for your level, you're just 1600 1500, but now if you see, to solve it, it's being too direct. To solve it, implementation also won't be too difficult, right? Because you can do often, you need not worry about complexity. Find the diameter somehow, find the best path, that's the whole solution. And then you remove them. Once you remove, you don't touch them at all, let's say. And then you remove them. Yeah, I'm trying to see, once you remove, should you remove them from edges also, or you can just mark them as yeah, see, this is a shitty problem, because you know why this is a shitty problem. If someone is worried too much about complexity, they may not think of, if they not think of enrouten, they may think, I can solve this, I'm not able to solve this. Maybe others who are solving it are using some great logic that I'm not able to think of. You will think that if you're not able to solve it, if you're not able to come to the complexity. But see see how all the problems you solve won't involve anything later. So now let's think about the complexity problem. What I'm trying to look at is, once you remove a vertex, should I remove its edges too, or can I just mark it as not visited? Can I just mark it as not visited? Is what I'm trying to see. So our our so what I'm trying to see now is, that's, should I remove it from edges of remaining vertices? Because for this we have to maintain edges as set of set, right? Instead of vector, we have to maintain them as set if you're removing. Or I can just mark that vertex as removed and not explore it. So if you see this thing, okay, if you see this thing, if you don't remove that edge, okay, if you don't remove that edge to V, you may approach this edge you may touch this edge at max 2 root n times, because our steps would be at max 2 root n times, I guess, right? So this edge between this removed vertex and to some subtree means that subtree has been operating at max 2 root n times, right? You work on one subtree at max 2 root n times or root n times. So even if you don't remove that edge, the complexity would be just m root n, which is n root n. So we need not even remove that edge. What I'm again trying to show is, if you use little bit of logic, you can be sure about of your implementations too. You need not worry about removing the edges and all. You can just mark the vertex as, okay, I can remove this thing. So now it's even simple, right? It's even simple. You can just find the size of the vertex. As long as the size is greater than 1, find the diameter, remove the diameter. Done. If the size is 1, you need not explore it again and again. I mean, you will remove the size is 1, right? So as long as you have not removed something, keep exploring it. Simple. How to turn on subtitles? Bro, how to turn on subtitles? So I will also implement this for you, Vedant Pandey. Uh, but you have learned something, right? You have learned that 2100 is not out of your logic, right? I don't know how to turn on subtitles. How can I? Damn, what the fuck is this? Hey, hey. Are subtitles working? No, right? They're not working. Hello. Bro, it's not working. Sorry. So now we can just mark that as that, and then we have to find the diameter, and then we have to just remove the diameter. So yeah, so we have to find the lexicographically maximum diameter, right? So many times in finding diameter, we use something like, we take some vertex and then find the farthest leaf. And then from this farthest leaf, we will find the other farthest leaf. That will be the diameter. This is some logic. Maybe we can try to understand it from here. Okay. Uh, so to find some diameter or to find the center, uh, if you take some vertex and try to find the farthest leaf, okay, farthest leaf, if it's, let's say that vertex was here, so if you see the diameter, farthest leaf will be among among these things, right? For sure, because it cannot be on this side. If it is on this side, it cannot be that far. It can maybe be here, but it won't be here too, because if you see, this itself is less than or equals to some L or something. So I think it cannot be here too, because this is less than or equals to L. And then you have just this much, but here this is L, and you have this plus this. Do you get what I mean? This is less than L, and then this is also less than L. So that if you see the farthest point from any vertex, it will be among here and among these things. So from some vertex, if you find the largest, the farthest, and also the largest, if you find the farthest comma largest vertex, you will have the best among these things that you want. And then from that, find the farthest and the largest, and then you will have that vertex too. If you have those two vertices, you can just remove that path easily. So diameter is also not a concept here. It's just simple logic again. You don't need much of diameters concept. See, I will tell you one thing: the amount of intelligence you have, or the amount of logical thinking you have, is all it all depends on how much you are willing to try. If you are willing to apply logic and try to understand something, that means you're smarter, or you can do things much better than others. Because you may go, okay, I need diameters code from somewhere, I need diameters concept from somewhere. You can think that, or you can think, okay, how can I understand this? How can I okay, I heard something like, to find the diameter, from this we find farthest, from that we find farthest. How can I prove it? How can I prove that thing? How can I understand it well? If you think of those simple things, we can see how we can understand it well. How I proved it, you can see this plus less than L is definitely less than this plus less than or equals to L, right? Yeah, it's the same advice I'm giving you, right? Not just to candidate master. It's the same advice to have a path in which you can keep increasing your problem solving skills, in which you can enjoy the problems, in which you can become high rated, or you can just use these things in your journey however you like. So Vedant Pandey, so you can see that we are not even finding the center now. Do you get what I mean? From some vertex, we find the farthest plus largest value. And from that vertex, we again find the farthest plus largest value. Right? So now how difficult is this to code, Vedant? It's a simple DFS, right? How difficult is this to code? It's a simple DFS. Simple DFS. So let me try to find that. Okay. I need a DFS. So let's see how I code. Hi, friends. We just solved a 2100 problem. I think the stream has been good so far. You can revisit. You can re-see the stream. It has been good so far, because it's simple direct problem it is. I don't know how it's 2100, because I know 26, 2700s are also not out of anyone's thinking or try, because but this is too direct, and Vedant is getting scared of direct problems itself. So let's see my implementation too. What all we want is finding. So what all we want is this thing. Now we need, given a vertex V, find its farthest and then largest node. If we have this, we can take some vertex, find best on one side. Now take that vertex, find best on the other side. What do I mean by side and other side? Is one side and other side is one side. If you take some vertex, you'll find the best on that by taking this side. So yeah, So I will try to make this function. Okay. Mm, so let's just keep it here. Value. Let's just keep that. We want farthest length and this value, right? So when we are here, we have height h. If h greater than length, or I'll just write like this. So this is what we have to do. Once we have the height, we just have to make sure that if it is further, give first priority to that. Farthest gets first priority, and then largest node will get the next priority. So for int u a g j o p, let's also have that adjoint array. If u not equals to e, and so let me initialize few things. See, we have already proved that this edge from B to U will at max be visited uh, root n times or 2 root n times. So I'm just maintaining some removed array. That's enough. And not removed of U. Then explore it. Then we have to just find, not explore, we just have to find this thing. Done. See, we are done. So for int, let me take inputs too. Okay. So Vedant, are you scared of this thing? We need not be, right? I'm not trying too hard, but yeah, I'm making things clear, right? That can be the reason. I hope Vedant is following up. So while not removed a file, let's do that. So as long as I is not removed, let's abuse that vertex itself. As long as that's not getting removed, let's abuse that subtree itself. Okay. So we sequentially have all non-removed things. See, these are all good implementations, right? Instead of thinking, should I maintain a set? Should I just going over one by one? While it's not include, abuse it. While it's not removed, I can't make bad analogies here. While not removed of I, what should we do? First, do DFS. Let's do first DFS of I comma 0. Okay. So now what do we have? We have length and value. So we have one endpoint, which is, let's call it u. We have u. Uh, yeah, we have u. U is val. Okay. Now again do DFS from u comma u comma 0. Now we have v. So do you guys know what this u comma v or? This u comma v are the path, the longest path that we are trying to remove right now. Okay. And we also have d. D is just uh, of apples, right? So d is just len plus 1 is the number of apples, right? Because number of vertices is l in the subtree, in the sequence. See, Vedant, how simple implementations can be. It's me going too fast than you can handle it. That's why you're thinking it's lagging. I'm just joking. Fuck, it's lagging. Oh, sit now. This mic and Vedant. Hello. It's fine now, right? So Vedant, do you see how simple implementations can be? We already found our diameter with just one DFS. So now, what we should do? What we should do is remove these things, right? If we stored parent 2, if we stored parent 2, we can remove right now itself, because here we should now go over parents of v until u and mark them as removed. Let's remove them first and then add them. So we have u to v, there is a path now. If you store parent, if you go back from v, we will reach u. Now we want u to be bigger. So if u less than v, see, I have done this swap here and not here because this parent depends u to be the root. Here u was root. So I haven't swapped them before doing that. After using u as u, now I am swapping it because I know what is u. I should know what is u, right? That's it. See how How simple implementations can be. Bro, what is this error? Can you guys hear me? Let's ignore this thing. We are not scared of this error, right? Yeah. So is this the solution? Is it done? Just this simple thing. Is it done? See how simple things can be. But we get wrong answers because we want bigger things. Past. So you guys should not think I am too bad. I take too much time. I can't all because you guys saw my implementation right now. How I have implemented while talking shit. I'll get some water. I have a question for Vedant. Do you think is this the only lucky problem that doesn't use anything? Yup. See, we didn't use great idea here. We utilize the fact that diameter length is reducing or we are removing many things. If length is small than root n, it keeps becoming less, so only root n steps. If length is greater than root n, we are removing root n things. So complexity itself gives out immediately that okay, it's an n-root-n thing. People see five, people see this, okay, n-root-n, how can I use n-root-n? How can I use n-root-n? Okay, we're throwing off things. Okay, if the length is greater than n-root-n, we're throwing off root-n things. Okay, if length is less than root-n, maybe the length reduces all after each time. So they try to check that. Okay, once I remove this, will that reduce? Yeah, it reduces, problem done. That's how direct this problem is. And you're scared to implement DFS. And what is this? Is this a technique? Is this a technique using a while loop, as long as the subtree exists, abuse it? Is that a technique? Does this need like anything? So simple. Even removing, I didn't even write another function. I just made parent, and then I just removed that diameter because we already found the path to that. So see how implementations also can be simple if you increase your skill. Nice. So let's go to another problem. Right. We have just seen how simple. See, using the fact that things are getting removed. So if that length is more than root n, we cannot remove such things more number of times. If that length is root n, that length is reducing. If that length doesn't reduce, the problem cannot be solved. If because that length is reducing. So you may think when I say, okay, I thought that's getting halved, but then that's just reducing. That's just reducing to 12 minus 2, 12 minus 1. Just that fact is making us solve the problem. Just this small fact. So at this level, it's not even ideas. It's just facts helping us solve the problem. So if you go little bit higher rated, we have nicer small ideas that solves the problem. So they are actually nicer problems. Do you get what I mean? As we go higher ratings, there will be nicer problems which you can actually work on. Just because you cannot solve some 1700 that brute forces abusively doesn't mean you cannot solve 2200, you cannot solve 2300, you cannot solve 2425 any rating, because one guy yesterday solved 2600, right? Because he just tried it and then he has solved it without thinking that it's 2600 this problem. Also, I kept this in the group. You guys also can try sometime. Jay Patel yesterday has solved this all on his own. He has solved it all on his own. Even I have solved it. You may think I'm low rated, right? Yeah, I'm low rated, but I have solved this effortlessly, like 2600, but I have solved it like effortlessly. See, no concepts, no topics, just small logic, and then swapping things. How can we do that? This is swapping things. This is just if else, initial two swaps, and then this is three swaps per operation to sort the array. So these are simple things. So keep that understanding of, you have to learn concepts, you have to learn techniques. There's nothing like that. All you have to do is improve your problem solving skills, which is nothing but improving your ability to try when it feels like it's not, you cannot solve it. That's all it is. So now let's try the other problem. 1 hour 18 minutes we solve 12100. This is success for us. This is uh, too good for us. We haven't performed like this previously. So now 2200 in our string. And Vedant, can you keep up with this logic, or is it out of your level? This logic is nothing, right? It's not out of your level, right? 2100, and this is a shitty problem. It doesn't even have any good things. So 22 would not be any different, right? 23 would not be any different, right? So we are trying 2200. You guys keep saying something because sometimes the stream disconnects. Yeah. So now we are at some 22, some random 22. What should we try? Should we try this build an array? It has a bit lesser, so should we try that? Or should we try tree colorings? So what do you think these tree colorings will have? We need not get scared about that. It will be just logic. Do you guys get what I mean? It will be just logic. Believe me, it will be just logic. So let's try the tree colorings itself, because we have done a tree problem. Let's try the tree colorings itself. Okay. I don't like this educational round. Sometimes they will be more shittier than normal rounds, but yeah, let's try to read that. Also, this will have just logic. It cannot have concept. What concept can help us? Can you map each problem into some concept? You cannot map, right? You cannot map each concept, each problem to, okay, this problem belongs to this concept, this problem belongs to this concept. You can never do that. Consider a rooted undirected tree. So I think you are a bit more familiar now with trees, right, Vedant? Damn, we have two viewers. I think it's Prismax and Vedant. Maybe Ari dropped. So let's try to read this problem. Okay. So all of them dropped or what? Like the video, guys. uh, code forces. You can try on code forces, Shinobi. Part 3 is 192200. Part 4 is 21. So let's read this problem. Shinobi, let me tell you how to start with CP, okay? Is Shinobi there? Part 1 is from 800 to 1500. So how you can start CP is, yeah, I'm giving you one roadmap, okay? So now try to read this problem along with us and try to solve this problem along with us. That can do much than trying to follow a roadmap, okay? So let's try to all solve this problem and see how things will be at some much higher level than you are aiming for, okay? Consider a rooted undirected tree. Each vertex can be colored blue, green, or yellow. You know what's a rooted undirected tree is? Maybe you don't, but a rooted undirected tree is nothing but there is one root and then there is these things here. Okay. Such a thing is called rooted undirected tree. This thing is called root, and then we have the same structure. So the same structure again will repeat here. The same structure will repeat here, like that. So that's thing called a tree. Okay, that's called a tree. Because the same structure repeats in most of the problem, we solve something for this, for all this, and then we solve that thing for this. Like fine. Still, I also don't know DSA, bro. What's DSA? I just tried random problems on code forces. That's it. I never learned some course like DSA crash course or something like that from somewhere. So yeah, people, we are reading this problem. Right, let's read the problem. The root of the tree is green. If you consider all blue and green vertices, they are reachable from each other without passing through any yellow vertices. If you consider all yellow and green vertices, they are reachable from each other without passing any blue vertices. You are given an integer m. Your task is to calculate the minimum number of vertices in a tree with exactly m beautiful colorings. So we have something, we have to do something. So what is the problem? Because it looks complex, I think it's a good problem. Not complex because it has many things. It see, one thing is clear. We have to use logic. We have to use this logic. We have to use this logic. We have to find whatever they are asking using just logic. We cannot use something that's not given in the problem. We cannot ignore what's given in the problem. My hand is paining. Also, Shinobi. I know you. Also, Shinobi. There is Adcoder's beginner contest today. Try giving that. Okay. Hello, Shinobi. Okay. There is Adcoder's beginner contest. Try giving that. Don't ask me how do I log in, how do I make an account, how do I register for contest. All those things you should be able to figure out. Okay. Try finding contests, try giving them, try to think how you can do better, try everything on your own. Try to just explore. You can time pass. So is it fine if I try to go over the same problem, Ari? Let's see how we can solve this problem. Also, Shinobi, focus on this problem. Focus on how we will solve this problem just using the logic given here. So let's try to understand the problem again. That's not working. Yep. So we have this rooted tree, it seems. And then they are telling this thing is green. And then they are telling We have also blue vertices, yellow vertices. Okay, three colors are there. All blue and green vertices, they are reachable from each other without passing through any yellow vertices. So what does that mean? What does that mean? All blue and green, which means if you take all blues and green, if you look them as same thing, if you look all the blues and greens, they all form a they all form a group. They all form a blue comma green group. Yellow will only be somewhere down. Yellows can only be yellows will only be here. So it's like this, and then you have some yellows, because all of them, the greens may come here also, like they may come here also, but how you can see that as, it's like you have a green blue thing and then you have some yellow things attaching to that, some yellow vertices attaching, because you cannot have a green again here, because if you have a green, that green cannot be reached from this without passing through yellow. Another specialty of trees, you can have a unique path, because you can see there is only unique path because it's getting divided, right? So you can only have unique paths back to from anything to anywhere. Yep, bye. It's too much, I know, for you to stay. So, bye. Watch it later. 2201. We have Ari and Prismax. I think we can try to go 22 and then I will end the stream. Okay. Because 21, 22 is enough for one stream, I guess. I'm doing too many streams. I'll try to find something to do with life. Yes. Mm-hmm. All blue and green vertices. And then we have, if you consider all yellow and green vertices, they are reachable from each other without passing through any blue vertex. So we again have the same point. So now how can we see the same point again? Which means, which means, what does this mean? We have blue. All the blues and these things form a group. Also, all the yellows and these things form a group. Means, so let's say there is a blue vertex here, okay? If there is a blue vertex here, can that have a yellow vertex below that? No, because if that has a yellow vertex, all this would be, if that has a yellow vertex, that yellow to green must have a blue in between, right? So we can say such statements. If so, root is green. If there is a blue vertex, same goes for yellow. Till here, it's not that complex, right, people? Yeah. Yep. What the fuck is this thing? More than one ingestion is using the primary URL. So, is this implies and implies? We have to think about that now. So, if this happens that all the blue vertices has no yellow here, so they may have some green. Let's say, is this implies and implies? Means, can there be a green vertex in blue subtree. S if no yellow or present, else no. So if both yellow and green are present, then the structure is very clear. As Prism X already pointed out, the structure is very clear. Structure is fuck. How to how to do this now? So we have green, some green. So if there is a, let's assume there are both yellow and blue present. Okay, if both yellow and blue present, we have some yellow subtree. We have some yellow subtree. We have some yellow subtree. And if there is a blue, we have some blue subtree. We have some blue subtree. That's it. But if there are no yellow, then this is also possible. If there are no yellow, then it's simple to imagine. We have a green, we have some greens somewhere, some greens somewhere, we have some blues somewhere, some blues somewhere. There can be anything. This structure can be anything. Greens and blues in any way they want. Same goes for green and yellow. So these are the whole cases. If both are present, this must be the structure. If only one of them is present, that's how we are using implies and implies logic. So now if all these things stay true, it is implies and implies. So that's how it has been solved. If you don't use logic well, you may not identify this case, right? You may not identify this case. So we can use logic and we can see if things are implies and implies or not. Like A implies B, B implies A or not. I'm using thumb touchpad. Yeah. How many viewers do you have? Okay. From next time, I will try to use Excali. Okay. Okay. This gives CP feeling a bit. The font and structure. We have colors, we have background, stroke with opacity. Yeah. What is along with you, bro? I'm not. I won't be counted in viewer. So yeah, that's the structure. So let's see what's the problem is. You're given an integer m. Your task is to calculate the minimum vertices, minimum number of vertices in a tree with exactly m beautiful colorings. Damn. So this looks complex, right? This looks nice problem. This is a nice problem. We want minimum number of vertices in a tree with exactly m beautiful colorings. So this is a good coloring, right? So is there a restriction that yellow must be present? Let's see some example. Just one vertex. Yeah. Sometimes yellow need not be present. If you consider, so m is very small number, and m is very small number, and if you look at this case, this case of green and this itself has so many ways. So this itself has so many ways. It's like choosing. It's like 2 power n minus 1 ways. This itself has, without involving yellow itself, this has 2 power n minus 1 ways. If you involve yellow, again, that's again 2 power n minus 1 ways, because anything can be anything, right? So these two itself, if you use n vertices, this corresponds to 2 power n minus 1. That will definitely be there. Can you guys here follow me up? Hello, Prism X. See, uh, we can think of greedy, but we should also think if you can prove that thing simply or not. This is being something we can say immediately. If there are n vertices, we have 2 power n minus 1 bg things, 2 power n minus 1 gy things, which makes it 2 power n. Plus, we have to use, we have to see, even before greedy, we can think of how to use logic. We can think of problem itself. The problem says we have to find n, the minimum number, that whose minimum number for which there is a tree that adds up to, these things will come out to be m minus 2 power n. So there is a tree. See, we can keep tree structures as we like, right? So there is a tree for which we can keep that as 2 power n minus 1. So let's use logic itself again. Okay, for n, see, before greedy, let's try to use the amount of logic we can use, and then we can try to think about greedy. 2 power n minus 1 g comma, because if you go for greedy, we may miss our basic logic, right? We may not be able to use our basic logic. So first we have to use basic logic, because we cannot come back, but we can go from here to there. Coming back may take a lot of time, lot of mental energy too. Now, so yeah. So if this is the answer, if n is the answer to m, what can we say? Let's just think about those basic logic, right? If n is the answer to m, what can we say? Minimum number of vertices with exactly m beautiful colors. So what can we say? Uh, n is the minimum size to have m colorings, means n is the smallest to exist a tree such that number of green, yellow, blue all having colorings equals to plus 2 power n equals to m. Means for n minus 1, whatever tree you use, there is no, so this says a lot. So this itself says we can identify what all numbers we can obtain from this number g comma y comma b, probably. Once we know that, then we can say for sure that n minus 1 is not possible, which means, see, how am I using logic? We should be able to say, if you believe that proofs are simple, implementations are simple, everything is simple, uh, that we should be able to say that it's not possible with n minus 1. It's not possible with n minus 1 or n minus 2 up to so on. This makes us think of what all are possible with n vertices, what all values are possible for this sheet with n vertices. So we can think about this thing before trying even greedy, right? How's that? We can think about that thing. So size n, for size n, what are all the different possible values we can have? So let's look at one tree. Okay, there's no yellow color here. So root is green, right? And we have blue. So it's about, what is it about? Let's say everything is green. Okay, everything is green. So now, other than root, we have to select number of ways to select some. So now, so it's selecting some vertices which are not ancestors of each other, because if we are trying to select the topmost thing, the topmost yellow, what that means, there is no yellow among above that. If we try to select topmost blue, that means there is no blue among it, and everything below must be blue. So if we can select some vertices, like it's this thing, number of things we can select disjointly, and everything above will be green. All of that would be green up to so imagine that everything is green, and then you select some vertices which are not ancestors of each other, and then you paint some yellow, some that subtree is yellow and some other subtree is blue. So that's the value, right? Number of ways we can select these non-intersecting uh, subarrays. Somehow it's that thing. Okay. Yeah. So number of ways. What all can we get? What all different ways can we get? We must work on this because it wouldn't be too complex, I guess. So can we give any upper bounds to the values we can attain? Can we give any upper bounds if you think about that? Yeah, here, right? Can we give any upper bounds if you think about that? What are we doing here? Selecting a subset, right? We're selecting a subset, right? And then selecting, so it's selecting two subsets, because we color some of them as yellow and some of them as some of them as yellow and some of them as blue, right? So it's like 3 power n, so it's like subset 1, subset 2. So it's like we have two disjoint subsets, so three colors, right? If you look at this tree, green, if you look at this tree, green, single, 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 that will have 3 power n colorings, because each of them can be either green or blue or yellow. So the max ways to get three things is 3 power n. So 3 power n is possible. So if m equals to 3 power n plus 2 power n, answer is n. So see how greedy may not work. We have to work on problem. This is true, right? This is the maximum ways in which we can color a tree without any restrictions. We have restrictions, but we have a way in which there are no restrictions. So now we have some other thing called 3 power n minus 1 plus 2 power n is possible with n minus 1, right? Maybe if m falls between this and this, we must use this maybe. And this is the max we can get from n minus 1, right? This is the max we can get from n minus 1. So maybe that's just the answer. Maybe it works, but we have to prove, right, before implementing. Maybe that can just be the solution. Is there RE? But what if this is just the solution? Say with n, the maximum you can attain is 3 power n plus 2 power n, right? And with n minus 1, the maximum you can get is 3 power n minus 1 plus 2 power n minus 1. This is fixed. This is in the worst case. Maybe we can obtain everything in between just by doing something. Maybe. Can we see for n equals to 1? We have m equals to, I'm sorry, here there must be one yellow. At least there must be one yellow or there must be one green. So this has, sorry, it's just 3 power n. Because we have to remove, from this 3 power n, we have to remove all greens and all yellows. That has gone. So that is just 3 power n. So can we obtain everything in between? For n equals to 1, max m is 3 power n, n minus 1. For n equals to 2, max m is 3 power 1, which is 3. And for if the value is 3, answer is 2, because nothing smaller can give that. N equals to 3, max m we can form with that is 3 square, which is 9. So just this structure is giving us answers to these things. So now the question is, can we get everything in between? Can we get everything in between using n equals to 3 or not is the question. Maybe we cannot, maybe we can, we don't know. So that's the question we have. Maybe we can submit a wrong answer and see, but we can try to prove things. Yeah, sure. Then viewers seems weird, that's why I asked you. Yeah. So but this cannot be just this simple, right? But this is good information, because if m is 3, if m is 9, we must output 3, because it cannot be attained with any smaller things, right? So now the question is, can we have everything in between? Is the question. Can we have everything in between? So it is in terms of 3 powers, right? So can we have everything in between is the question. So we can see something. We can take a fact from here that we can take a fact from here that we can take a fact from here that we can have a green. We can look at these things, and then this having multiple things, and then we can take one more, and then this having multiple things. We can see such things, right? So what happens here now? If this is yellow or blue, that is two ways. So all of them can be green one way. All of them can be blue or green. That's another way. So there we have three ways. Plus, if you just look at such structures, plus if all of them has all green, blue, yellow, means this must be green. This must be green. And then this must be blue. And then this must be yellow. How many different ways is this thing? Also, this can be green, right? So we have, if this length is L, we have 3 plus 3 power. We can get 3 plus 3 power L by splitting these things. If you split into L1, L2, L3 up to so on, we can get 3 plus 3 power L and so on. Oh, Prismax, is that fine? So far here. I think if you can finish this 22, we can just take rest and end the stream. Is it fine till here? Yeah, it seems fine. Uh, Wait a minute. I want to book some cult group class kind of thing. It's like old people book group classes. Young people will probably go to gym, but I'm old. I don't have time. I don't have much time, so I will prefer this. It's booked. I'll charge my phone too. So now we have to see. Yep, I have to go. I have to go and work out a bit more to do a sleeveless. Flex my flex my muscles. Doing too much. Yeah. It's so difficult to hide all these things inside this shirt. I'm just joking. Uh, like I like that joke. I don't like that you are gay for me. Exactly, young beautiful colorings. So yeah. So here it seems like we have so much power, right? 3 plus 3 power L. If you see these structures itself, L1, L2, L3. If you split them like this, we have 3 plus 3 power L1, 3 plus 3 power L2 up to so on. So we have this much power again. Can we have some other kind of structures? We can even have one directly from here. We can also have these things too, right? Blacks directly from here. So those will be 3 power L again. So with all these things, can we have everything in between these two? What's in between? So we have 3 power n minus 1 minus. Can we attain all these things from 3 power 3 power n minus 1 to Can we have all these things using is the question. If not, we must use n plus 1 or so, right? Maybe if this cannot be obtained with this, maybe it can be obtained with n plus 1 or so. Because, haha, that's nice. So yeah, we have to somehow solve this problem, guys. So with this, we have this structure possible. So let's try to see. Let's try to see if it is not, if it is greater than, so we have greater than, so m being greater than 3 power, we have to guess, is this the answer? Can this be the answer? Then the problem will be too simple, right? It will just be about seeing what 3 power it falls. Oh, we can see test cases. That's a bad habit I have, not seeing test cases. That fucked my last contest too. If I have seen test cases, I would have done b much quicker. So 1 falls in 3 power 0, so answer is 1. 3 falls in 3 square, so answer is 3 falls in 3 power 1, so answer is 2. 5 falls in 3 square, so answer is 3. 7 falls in 3 square, but the answer is 4, so it's not possible. So we see again 9 falls, 9 for 9 answer is 3. So this test case itself answers that it's not monotonic. So trying to prove that would be useless. So a simple test case itself is answering us that. There were only two questions anyway, but last question, last part of the stream. Yeah, that's a bit sad. Not too sad. And you also missed my flexing, my me flexing thing. uh, yeah, so see, this itself proves that it's not strictly increasing. So we have to be more careful. We have to actually identify what all are possible with this thing. What all are possible with this thing. We have to actually identify that. Right. So one thing is clear. See, if you know what all are possible with size n, we can always write our tree in such a way that uh, one vertex, and then a subtree of size L1, and then a subtree of size L2, and then a subtree of size L3, up to so on. Now the number of different colorings will become what all ways you can color. So product of these things, it will become product of these things. Do you get what I mean? So taking one product from L1 thing and then taking another product from L2 thing, one possible values of product from L1 times some possible values of times L2 times some possible values of times from L3 and so on. This is possible, and this covers all the things too, in different ways of splitting them. What the fuck is guns? Mm, yeah, give contest not today. ABC, I won't give beginner contest because my rating will drop if I give beginner one. I can do better in regular contests, I guess. I may give tomorrow at Coder. So yeah, this is fine, right? This is also one statement we can say, because if you know all possible colorings of this, where yellow is allowed in the top two, all yellow or all blue is also allowed. We can get all different types of products with that. Is it always possible? See, sometimes it's impossible, but we have to see if it is sometimes impossible or not. Okay, we have to see if sometimes it's impossible or not. So let's try to work on it clearly, because we have to work from the beginning. What all are possible for size 1? So to generalize things, let's say yellow is allowed here too, okay? Because once that goes down, yellow is allowed here, right? All yellow. So 3. So like f of 1 is 3. F of 2, f of 2 is again 2 plus 1, let's say. 2 plus, uh, this 2 is the whole tree being yellow, the whole tree being blue. Okay. Now we have two things. If the top one is green, the below things can be 3. Uh, and we can have only these two are possible with f of 2. We have to finally subtract this 2 from things. So from 3, using 3 things, how many can we have? We can have 1, 2, 3. It's again fixed, right? Or 1, 2. So we can have, if the top thing is green, let's say this 2, if we remove that 2, this 2 is just all green and all yellow. Now the below 2 can be written as 2 or 1 comma 1. This is what I mean by L1 plus L2, L3 up to so on, all possible summations, right? So if it is 2, we can have f of 2, which is 5. If it is 1, we can have all possible 1 comma 1. 3 times 3, which is 9. If it is 1 comma 1, what we have is 3 times 3, because this can be 3, this can be 3, right? Sometimes it may be impossible too. That's why we are trying to see what all are is being possible. So answer for 5 and 9 is 3 in this way. You see, because this 2 is not in the answer, right? Total green and total blue is not allowed, right? Teja Drona, I guess. I may not give today. Yep. My rating is not high here. Here I did second in country, I guess, below dominator, but again it's bad. So guys, we have to be careful. Maybe after some point it will have everything. Maybe it will never have any some things. So we have to work on this little bit. So let's see, because here itself the answer is complex, right? For 1 2, so 1 3 5 9, 1 3 5 9 is there. 7 itself is not there in 3. So if you see f of 4 now, 5 comma 9 is there. This is 7. So these two we should remove while outputting the final answer. Okay. But looking at f of 1 is more important. Looking at these values is more important, because these things are what will get multiplied in the before, in the below. Do you guys what I mean? So if you see at f of 4, 2 plus being same blue, total entirely being green, yellow entirely being blue, plus how many ways we can write 3 as? 3 or 1 comma 2 or 1 comma 1 comma 1, right? So looks like we can brute force everything. Because for f of n, values of f of n are greater than or equals to 2 power n minus 1 and less than or equals to 3 power n minus 1, right? This is true, right? So how many different n we can have? Guys, we are getting the solution now. We're thinking that it's just brute force. After observing a few of some small things, because of this lower bound, what do we have is uh, because of this lower bound, what do we have is n must be less than or equals to, sorry, whatever the answer n, 2 power uh, so 2 power n, we can say our for our n is less than or equals to, because for our n, so let's say nub upper bound of n, we can have this upper bound of if m greater than or equals to, if m less than 2 power nu minus 1, this is an upper bound. Is that clear? Is there people or are people following? So even here, if you give importance to m being 5 into 10 power 5 and not being 1e18, that shows that this is brute force. That shows that this is brute force. Do you guys get what I mean? Because if it is some log n solution, we can solve the problem for 1e18, right? But this shows that it's some brute force. Yeah, I'll go Susu and come back. Meanwhile, you guys can see maybe we can brute force all the things. Maybe we can brute force all the things, right? Uh, because we have this upper bound for m. We have this log n upper bound because from answer cannot be above this, because if answer is above this, it's no way to achieve this thing, right? So that lower bound that we initially found, that it's at least this much is already there, that is itself helping us a lot. Just this statement is helping us a lot. See, just after writing this, we can say there is an upper bound, there is a lower bound for n. Like if you keep, let's say it's not possible at 1, 2, 3, 4. We may have hope, maybe it's possible at higher thing. There is no hope because at least this much will be there in all the higher things. So we have an upper bound for that. And if you see that's just log n, means nu equals to 1. What's log n here? 5 into 10 power 5. So what's 2 power 20? 2 power 17. Sorry. 2 power 18 doesn't work probably. So 2 power 19 works. So 2 power 19. So let's nu is 20, less than 20, because nu minus 1, right? So n must be less than 20. So because it's just 20, maybe we can brute force all possible values less than or equals to this obtained from f of 1, f of 2, f of 3, or obtained from product of few things. All possible values you can obtain from product of few things is what we need. Because if you store uh, not just f of 1, f of 2, and f of 3, we also need so yeah, this is getting solved. So who is following? Ari is there, right? So if you see that f of n, answers will be less than 20. But if you see f of n, it is 2 plus. Now you have n minus 1 things, and you need number of ways you can split this into L1 plus L2 up to so on, and you take distinct values that can be formed by product of all those things. So a value can be found with L1, a value can be found with L2 up to so on. Let's say you need this set now. You need this set of V such that V equals to V of L1, V of L2, where V of L1 product, where V of L1 belongs to f of, these are sets, right? F of L1, V of L2 belongs to f of L2, and so on. Because these can be split into many ways, let's not have them. Okay, let's define a state called G, because all these things doesn't matter, only that sum matters, right? So let's define a state G, where G of n will be, I am maybe complicating things, but yeah, where G of n will be values that can be obtained with V equals to, we also have L1 plus L2 up to so on equals to n minus 1. Okay, here L1 plus L2 up to so on equals to n minus 1. So V equals to V of L1 times V of L2 times V of L3. So this DP works. You guys can see that. Fuck. So what am I saying? I wrote a lot. So f of n is uh, we have one in the top, two things total yellow, total blue, one at the top, and then we have n minus 1 things below. Now we have to find number of ways you can split these n minus 1 things into L1, L2 up to so on. And then what we can take is V of L1, a value that's possible with L1. V of L2, a value that's possible with size of L2. V of L3, a value that's possible with size of L3, up to so on. That's the structure, right? That's the structure of all possible values. So I wrote them as a set. What all values are possible? 2 plus, damn, some pretty girl is passing by. I have to look at her. Damn, she's really pretty. Yeah. Damn, bro. Not so often beautiful girls pass by this place. Yeah, where are we? Uh, so where do I stay? I stay somewhere here. We have people walking around. That's the reason why I was looking outside. Yeah, I hope no one noticed. Is this fine? Whoever is there. So V equals to V, where V of L1, V of L2, so on, the product of these things, where V of L1 belongs to F of L1, because all the possible values attained by L1. V of L2 belongs to product of L2, and so on. But now we can split many ways, right? L1, L2, we can split in many ways, but only this sum matters. Only that sum matters. So what we want now is only that sum matters. But I think if you think about it, all possible values that you can obtain from this sum, like I tried writing them as some other thing called g of n. I tried writing that as g of n. Okay, let's write it as g of n. But if you think about it, we can write g of n as f of n minus 2 or something like that, I guess. I think we can write it like that. So let's say g of n as v equals to v of L1 so on L2, where guys, is this being fine? Ari, is this being fine? We can end the stream by 2:30 or so if we can solve the problem. Yeah, so where v of L1 belongs to f of L1, v of L2 belongs to f of L2, and so on. Okay, you can see this relation. This is almost same as this relations, right? Like if you see that g of n, I mean, it's almost same as this set, right? It's just that here you have to split. Here sum of L1s add up to n. Here sum of L1s add up to n minus 1. So g of n is nothing but. So what is this thing? This is g of n minus 1. This is g of n minus 1. So g of n is v minus 2, because the 2 gets additionally added, where v, so where do we have g of n? If you look at f of n plus 1, if you look at f of n plus 1, we have 1 in the top. Now n gets divided into product. Because of 1 in the top, we have 2. So f of n plus 1, we have 2 for every element plus g of n. Right? So g of n is a set. That's why I'm writing it in reverse way. So g of n is where v belongs to f of n plus 1. Is this being fine? So all the values of this, so it's just utilizing the previous things. So now how do we get f of n is, we brute force on L1. We fix L1. And then we go and check what are all the things that are there in among all these things, and then we take their products. This seems fine, right? Brute force. But then, how can we take product of these many things and then these many things? That seems a bit big to do, right? That seems a bit big to do. But maybe it works out. So for f of n now, 2 plus, let's say L1 comma L2 is what we split into. Okay, L1 is f of L1 times L2 is let's keep equals to n minus 1 g of L2. L2 being product, how many base you can, how many different values you can have. So we have f of L1 plus f of L2, all these things you want. And what is g of L2? It's just nothing but, so you have L2 less than n minus 1, right? So L2 is less than or equals to n minus 2. So g of L2 would use f of L2 plus 1, which is less than or equals to n minus 1. So we have that information already. So g of L2 is nothing but f of L2 plus 1 minus 2. But how can we get all possible values from this and from this? That seems a lot, no? But we can use again root n logic a bit. But then are we doing 20 times root n times root n? Maybe it works. 20 times root n times root n, maybe it works. 4 test cases, right? So what I mean is, if you have f of L1 and f of L2 plus 1 minus 2, root n, see, only for the first root n values, we go until the end. But after root n, we don't go until the end. We go only till root n values. So in that way, it's like n root n. At max, we touch n root n things. Is this clear? So let's try to brute force. It's even better than n root n, I guess, because maybe it's even better than n root n. So let's just use just this logic that f of n equals to 2 plus f of L1 times f of L2 plus 1 minus 2. See how I make simple everything into simple formula. So we just make f of 1 now, f of f now. Or is there a better way to implement this thing? Because when m is given, we should again check if it okay, if we find all f of 1 f of tops on f of 20, we can just go over all of them and then check if something comes at some point or not. Pre-computation, we can do that. So let's try to just do this f of n then. Should I use set? F of 1 is 1 minute. So this is also a shitty brute force problem, right? Also, this doesn't have very good logic. All these problems are like that. Like that. F of 1 is 3. We have our formula, this formula. Maybe this can be simplified too, but for now, let's just try that. Let's go over. Let's say if it's just the one thing, if it's just a one thing, what would it be? F of L minus 1. So, so if it is only one L1, there is no L2 at all. There is only one L1. That is nothing but only one thing. Number of that is nothing but f of n minus 1. So go over all f of n minus 1 things, add 2 plus v to that because 2 is here. I mean, I am using a lot of logic effortlessly. Yep. Also, I don't like that. See, I am using things effortlessly, but that should not discourage you people, I guess. Two plus f of L1 times. So this brute force should work, but is it too much? Let's make them vectors. The complexity. But then we have to make them unique also, right? But again, this affects complexity too. No option but. See, this may go over complexity, but it's a correct solution at least, right? It's a correct brute force solution, at least. The only problem for us is this one, but can we do anything? We cannot do. We should brute force, right? We must brute force. We cannot do much about that. Maybe, maybe, Maybe if you assume that L1 is the smallest thing and L2 should have in among its splits everything greater than or equals to L1, states will become more, it's even more complex. So this break is enough to do that. So it is like now 20 times 20 times n root n. Shouldn't work. So now let's just push back into our vectors. It's sorted because it's a temp, it's sorted. Because all green, all yellow, and all blue are not our things. Damn, it ran. It ran quite quick. We are good with this then. It's a wrong solution, but it ran quite quick, Ari. If you're not making some big mistakes, it's done. I'll go to washroom and come. I told before. I will come in 5 minutes. I will some straight. You can charge. Hi guys, I am back. Maybe our formula has some error. Maybe because I just wrote it randomly, right? Maybe our formula has an error. Maybe. Hello? Yeah, you're there, right? Sunlight is coming. I have to form use it properly. So yeah, we can just try to debug now because it seems we don't have too many values. in f of n. What is f of 2? F of 2 is just 5, right? Let's verify f of 3 itself, okay? One day, maybe someday, in a bad orchestra. Oh, okay. F of 3 is right. Now, f of 3 itself is wrong. It is 2 plus 5 comma 9. Why is it 5? F of 2 is 5. And f of 1 into 1 is 9. F of L2 plus 1, right? V2 minus 2. 7 comma 11. Is that right? That doesn't seem quite right, right? Okay, that is right now. If we solve this, we can end the stream. Ari. It's difficult, but let's see. For 1, why don't we have 1? How is it minus 1 for 1? It cannot be right. One, 2, 3, 4, 3. And it took very less time. So I think this will pass. Do you see how I make implementations very simple? Always. Fuck. How can we get a wrong answer? I am just saying now. Oh, 20 is possible. Fuck. Where did we make a mistake? Wait. Did we make a mistake? 2 power 20. Wait a minute. Is this wrong? Guys, tell me, how is it possible for 20? If you use 20 things, we must have, we must have 2 power 19 plus 2 power 19. How can we have 20? Wait, is it wrong? Is it entirely wrong? Ari, I don't look like it. Don't. It doesn't look like I have considered those things, right? Where we have all green. No, where we have. I think I haven't considered them. Where we have green, blue, and then again green. Those things I haven't considered. It looks like we should not consider them because in my repeating formula, in this formula, I have only considered two things, right? Once, wait a minute, we have green, blue. For n equals to 20, it starts with 2 code 20 things. Because if you look at, bro, is it all gone waste now? See, bro, GGB is there, but GBG is not there. Consider bamboo tree. GBG is not there. So their problem statement has a flaw, right? This definitely has a flaw. Do you get what I mean? Yeah, exactly. No, see, their problem statement has a flaw. It's not allowing. It's not allowing B, GBG, B, G. It's not allowing that. But what rule prevents that? No rule prevents that, right? But it's not allowing GBG here. And it worked because even we didn't allow GBG in our recursive formula. We didn't allow that in our recursive formula, uh, but we allowed it in finding lower bound. So this 2 power n minus 1 lower bound is wrong. What is the lower bound for f of n? It's NC3 now. See, GBG doesn't violate this thing because yellow vertices is not there at all. Also, this rule is correct because damn, this rule is failed, bro. Fuck. What is logic? When there are no yellow vertices, this rule is failed because this that's not right. Core forces problems cannot have flaws. They are very good. So you see how this rule fails. I thought when yellow is not there, we need not consider this at all. But when yellow is not there, this rule still applies. Consider all yellow and green vertices. Blue cannot be in between. Fuck. Do you see that? Damn. We should be very careful in logic, I guess, right? Hope you liked the video already, Ari. You would have. So now this cannot be there. So now what would be the limit? Maybe our brute force still works. Otherwise, we cannot have logic, I guess. 7 works and that doesn't work. I don't think there is good enough logic here. Can we have some other upper bound? Somehow. It's NC3 is an upper bound, right? NC3. Let's consider the worst case. Uh, let's consider the Yeah, that rule is violated, bro. GBG violates. Consider yellow and green things. Then blue comes in between. That's just damn, right? I thought if yellow is not there, that rule doesn't matter. But then that rule matters even if yellow is not there. See, we should be very careful with logic somehow. Carefulness is important. Now where are we? Where are you now? Now where are we? Yeah, let's see if there is some other lower bound. Let's see the bamboo thing. How many different we can have? We have green here. It's just n ways. It's just n ways. If you see bamboo, it is very low. Maybe after some point we can attain everything. Maybe after some point we can attain everything. Maybe. Uh, so maybe after some point we can attain everything. So let's just think about it some more time, because this brute force is not wrong. And if brute force is, if there is some other solution that's not brute force, then there should be some pattern among these things, right? Some nice logic among those things. But I don't think we have any nice logic among those things, right? It's a weird structure. So either after some time everything is possible. Either after some time everything is possible, right? So let's try to see that. Or there is a lower bound. Damn, 25 itself is taking too long. Brute force doesn't use any logic, but if it's not brute force, what can it be? It should be brute force only, but can we get another upper bound? No, I guess, right? Because for bigger values of n, we can always have 2n is an upper bound for values of n. But that doesn't help us at all. So if you see bamboo, like the bamboo thing, it always has 6, 2 into n, plus or green. So let's look at bamboo. Bro, it all became different because I consider 2 power n minus 1 as some upper bound. But now if that is not allowed, then see, green is top. Now among n minus 1, yellow can start somewhere, blue can start somewhere, 2 into n minus 1. Plus they are not starting anywhere. So we have 2 times n minus 1 equal to m. So we have m plus 1 by 2 is always possible. So now if we use these kind of things, can we have can we make anything out instead of brute force? Maybe if we try to use these kind of things to make values, maybe just missing that was everything, bro. We have to we are solving the problem again. It looks like we're taking too long, 2 hour 56 minutes. Fuck, taking too long. If I have solved it alone, I would have solved it much quicker, I guess. So I think now we can consider these things of like take one thing. These things will give too many things, I guess. If we consider these kind of values, we have L1 times L2 times L3 times L4, which says if you look at prime factorization of some number, if you take only one, that will have green or yellow. Two, right? That will have two. But what the fuck was that? If you take three, so it is always two into one. If you take that, it is two into one. So I think see, now it's symmetric, right? It's symmetric. Because it's symmetric, m must be even. So small observation, it should have been our small observation. One minute. One minute. Uh, so this is clear. All green will always be there. So for everything else, if we swap blues and yellows, we have a pairing, right? We have a bijection between all different blues and all different yellows. If we can just swap them, we have that mapping, right? We have that mapping. So all these are even because once you swap blues with yellow, whatever comes, we can pair those two things. And there are no symmetric elements because once you swap blue with yellow, they cannot be equal. Blue became yellow, it cannot be the same element. So M must be odd. And once M is odd, so M is odd. M is odd, right? Ah. Once M is odd, no, now what I'm trying is, again, is there a lower bound is what I'm trying. Because if M is odd, let's say all green is 1 again. So now we are looking at even thing. If you're looking at an even thing, we can divide it by 2, some number of 2's, let's divide them by some number of 2's. And then what do we have? But then if you have multiple branches, it will be like blue or green, blue or green, blue or green, blue or green. So 2 into 2 into 2 into 2. So we can have those 2's, right? And then let's say if it is, so it will be product of few values, right? It will be product of few values. So we can always have, we can always have, we can always have this thing. So see guys, so for all odd values, we have M plus 1 by 2 as a possibility, right? So for all odd values, this is a simple possibility. So now for all odd values, 1 plus p1 times p2, it's even, right? It's even. Now it's even, right? All being green is one thing. Now we have things becoming, let me take a moment. We have things becoming, I mean, if you take these lines, it's like 2 times L1 is possible, 2 times L2 is possible, right? So I'm trying to see prime factorization. If you can see prime factorization P1, P2, P3, can we, for product, can we get sum as an upper bound? But then these 2's are coming in between. But it's being too much today in the stream. Ari, do you get what I mean? If you see prime factorization, we can always attain 2 times P1, 2 times P2, but wait a minute, not 2 times P1. Let's think of it again. So what is the answer for this? This is green, and this can be 3, right? It's all green or blue or green. Let's take something else. For this, what's the answer? All green from here, all green, or yellow started from here, yellow started from here, yellow started from here, blue started from here. That's again 4. So 5. So this will have 3 ways. This will have 5 ways. This will have 6 ways, which is nothing but m plus 1 by 2. So for 6, sorry, for 7, 7 plus 1, 8 by 2. So that will have this one because all green, yeah, because there is no restriction on this being yellow, right? That's why the formula became better than this. So now it's clear. What's the max value now? It's always possible within P1 plus P2 plus P3 up to so on. If you take prime factorization, That's always better. And now if something exists, that's not prime factorization. For this odd number, for this odd number, all green is not a thing. All green is not a thing. Let's leave that. Because all green is already considered among this being all green, right? Among this being all green, right? So when all of them become all green, that's already considered. So now the answer is just all yellow and all blue are not there. So the answer is just nothing but for this odd value, it's like some value of L1 times some value of size L2 times some value of size L3 times some value of size L4. So if this is not a prime number, then we can remove that into prime numbers, and then we will probably make the value lower. I think we'll probably make the size lower. So is it just taking prime numbers and then adding prime factorizations and then adding their answers? 7 is prime, right? So take for 7 answer will be m plus 1 by 2. We haven't made this logic very clear, but maybe that works now. We haven't made this logic clear, but yeah, how difficult is it for me to again implement them? Prime factorizations, right? Int LP. Let's say this is some lowest prime that has in there. So let them be 0 initially. I mean, we have to be clear about the proof of this, what we are applying here. What is the, let's say in that product, this is not a prime number. We prove that, let's assume inductively that if this is not a prime number that's coming from uh, here, let's prove that it's always better to split that into non-disjoint prime numbers plus 1. So this would have always been the optimal to attain that prime number thing. But then instead of keeping this here, we can keep this thing into top itself. So that makes sense, right? To attain this value using least amount of things, this is the optimal thing using prime numbers. But then why keep it here itself? Keep them above itself, right? So maybe that works. Maybe that prime number answer works always. So should I just, we haven't proved it clearly, but I don't have time. So let's try to assume that it's like the biggest prime, I guess, that divides it will get stored in there. So this is always possible, right? If it's not a prime, let's say the best way if it's not a prime is to split that into one prime factor, and then splitting remaining things into some other prime factor is nothing but just this thing. So answer is dp of I equals to dp of, I need not even apply min. If that's not a prime number, then what should we do? Let's say this is the minimum thing. Take that prime number and then take that prime number. A minimum number of ways to split into that. Maybe that's the answer. See how important it's to solve problem. Maybe this is wrong, but still, see how important it's to solve problem, read problem correctly. If you make one mistake, it's fucked up. The whole contest would get fucked up, right? Something turned me on, smoking made me. What is fucked now? Maybe we should have been more careful about them becoming yellow or not. Because the same formula is not enough. We can have a better formula. See, what I'm trying to do here is we have a better formula. It's not even I plus 1 by 2, it's I minus 1 by 2 because we can start with top itself now. We can start with the top itself. So it's like I minus 1 by 2. So, which is nothing but dp of I minus 2 because minus 1. Bro, I am also not doing it correctly. I am making many assumptions and so. But give me a minute. Yeah, let's try to submit this and check. I should be better. I should not do this guessing things. So for 11, answer is 4, it seems. So it's not into primes. Should I stop here? But no, I cannot stop here. I get it. Oh, let's just look at 11 because that may clarify us things, right? 11. 11 can be obtained by using just 4, it seems, which is 1 and then having 3 things here. How? Bro, 1 minute. 1 minute. 1 minute. Let's make things a bit clear. So, because I have made many assumptions even with this formula, right? So, let's make some things clear. So, for 11, let's try to make things a bit clear. So, we have, let's just be dp of, let's just assume that we will find for, we will allow, let's say we will allow all green and all yellow too. Okay, let's allow all green and all yellow too. Okay, because that's how we use in recursion, right? So if you allow all green and all yellow too, what would be the thing? Plus 2 will come here. Okay, now this is a possibility. So now for 11, to obtain 11, what can we have? 11 is like 13 now. To obtain 11, so 11 is nothing but, హలో మా నేను అన్నం తిన్నామా పనిలో ఉన్నా మళ్ళీ కాల్ చేస్తా. So what do they mean? If you consider 11th expected 4, right? 1, 2, 3, 4, 5, 6, 11. Expected is 4. So let's once see how with 4 vertices we can achieve 11, 13. 11 is 13 because if you are allowing all yellow and all green, it's 13. So now let's see how we can get 13. What did I say? I said that this should be equals to 2 plus product of few things, right? All green, all yellow. But if it's not a product of few things, it's just one thing. Still, can we just have 4 things in a line? This would be not 11, right? This can be green, this can be yellow. 3 to 6 plus 7 it is. How can we have 11 with 4 things, bro? Again, do we miss something? So we can have 27 with 1, 1, 1. We have with 1 now, for 1, what will be the answer now? Uh, but we need 11 ways, right? See, 11 was possible with. No, this is not. So 11 was possible here. In our original code, 11 was possible here. From where would it have been possible? Taking 9. So just taking three things will give us 11. Maybe there. And what is this three things? It is 1 comma 1. So this will give 11. Yeah, this will give 11. Because we can have 2 plus all yellow, all blue, plus if it is green, we have 9. Right. How can we see this thing? 11 is one thing. So dp of 11 is 2, is just a line, or so that thing, I think we can use the same thing, same logic for. Damn, I wrote this logic with nothing on my mind, like thinking. It's like intuitively writing that logic, I guess, right? When I wrote this thing, I wrote it almost intuitively, like okay, one is on the top, and then we have these things. So but yeah, that can be applied onto the top below thing too, I guess. Still it's wrong. We can stop here, I think. So this is nothing but, because now it's not just prime factorization, it's like p minus 2. Okay, this is prime factorization. We have one. We split it into prime factorizations. For prime number p, we are having it's it's optimal. Maybe this prime assumption is not true. Guys, let's leave it. It's becoming too long. Maybe I can try later. Should I try some other? Maybe I can solve some problems in 5 minutes, bro. Sometimes some 2200s I can solve in 5 minutes. See, if you see this one in contest, I might have solved it very quickly. No, not that quick. Say, Ari, bro, it's too late, right? So, we have one. We have few things, right? We must make this into divisors. And then, if you look at other things, all of them combined are giving us some other divisors. But then, that is just dp of other divisors. But this is dp of this minus 2 because here two things are allowed. Yeah, let's brute force that. I don't know how to use divisor 1 because divisor 1 we can never get the product 1. Yeah, understood how to get the product 1. It's fine. It's fine. So let's take the divisor that's not 1, okay? And we're assuming this is being somewhere. And if that's being somewhere, from top everything else is see. I will tell what I'm doing now. We are going over all divisors. So, Ari, just follow this. I think we are almost done. Ari, are you there? So, let's say one group is contributing to our answers. This is green. There's no change. So here, let's say this group is contributing to answers. Uh, Divisor D. Okay. All of this will be M by D because all of this is M by D, right? minimum ways to see green is already there, but here all of this can be blue or green. So this should be dp of d minus 2. So dp of m is minimum of, we already have these answers, right? dp of m comma, this is what we are brute forcing, but then we should do minus 2. That's why I'm not choosing 1 dp of d minus 2 plus, and this is already fixed, which is dp of m by d. This must pass. We are brute forcing too good. See the fact, I should not have brute forced here. I should have thought that this value is dividing. This v of L1 is dividing. This v of L1 is dividing m, right? If it is dividing, I think I should have brute forced in that way, I guess. Right. So this was stupid. Here I made a wrong mistake. See, I made this because I thought the value is bounded. Otherwise, I would not have gone this much deep into that, right? If it is not bounded, then this is not the type of brute force we do. If it is not bounded, we must find some other way, and which is this way. That trying to see a recursion in there. It's still wrong, but we can correct it for sure this time. So it was just finding a recursion, finding a recursion. I complicated a lot because I thought there is a lower bound, but then there was no lower bound, and it's just a recursion. A recursion is an easy recursion, and not that difficult recursion too. What did I change? If m is even, it's definitely zero, and if m is odd, we are brute forcing over all possible divisors. That's done. So all of these are like brute force problems. So if there was an m, that would come from here, right? This divisor, and then all of this seems fine because for m by d, green fixed, that's the number, that's the minimum tree we can attain. But for this, extra two things are there, all green and all blue. Because all green and all blue are there, so I'm subtracting those two and then I'm taking dp of that. Is that fine? I think that seems fine, right? Wrong understanding of question costed us a lot of time. It all started because of that, right? It all started because of the 2 power n minus 1 bound. Otherwise, if that bound was not there, I would not. We could have just seen the whole structure. I think. See again, what's important is seeing the structure. If you see the structure that it has L1 times multiplied by L2 times multiplied by L3 as subtrace, then itself we can do this somehow. That there is repetition and divisors are not much. Okay then, bye. This is too much.